So students, welcome to the class. So today we will talk about uh, some introduction to modulation, as well as we will also introduce amplitude modulation in this class. In the previous classes, we talked about the block diagram of electrical communication system. We also talked about the concept of modulation, and today by continuing with that concept of modulation, we will move to amplitude modulation. Fine. Hope all of you have read the material from the books also in the previous classes, and you are following what I am delivering through this class. So firstly, I'll briefly touch upon what we talked about modulation and the detailed block diagram, and then we will move to amplitude modulation. So dear students, if you remember, we talked about the detailed block diagram of communication system, where I talked about the transmitter, then the channel and the receiver part. And the most important block in the transmitter is the modulator, where modulation will take place. And in the receiver, the most important part is demodulator, which we also call as detector. And the third thing is the main culprit, that is our channel, which will make things difficult for any communication engineer. So we are mainly concentrating on modulator and demodulator part. Okay. And in the previous classes, we also briefly touched upon what is the purpose of encoder and what is the purpose of decoder. Next. Then we discussed about modulation and demodulation in brief. Okay, so the main points that I would like to re-emphasize, I have underlined in this slide. Okay, so one thing that I want to reinforce is that modulation is a process which makes a signal compatible with channel. I have again and again explained in the previous class that modulation makes our signal compatible with channel, or modulation matches the characteristics of the signal with that of the channel. Our objective is to make our signal travel through the channel, and the traveling will be possible only when your channel and the signal, modulated signal, they match with each other. So these are the two main points, or in fact, I will call these 2 points as the conceptual definition of the modulation. So conceptually, we can say that modulation is a process which matches the characteristics of the signal with that of the channel. Okay, and rest of the points that I have already deliberated upon in the previous class. And demodulation, we already know it is the reverse of the modulation. Okay, now let us move forward. So we have talked about in detail about the need for modulation. Just to recapitulate, I'm mentioning this thing that is your need for modulation. So as I just talked about, modulation makes our signal compatible. Then we know that high frequency signal is able to carry itself for longer distances. So with the help of modulation, we shift the frequency of the signal to higher value. Then because of higher frequency, the height of antenna required after modulation will be smaller as compared to without modulation, that we also talked about. Then with the help of modulation, we will provide unique identity to each information signal, and with the help of modulation, we will assign unique carrier frequencies to each of the modulating signal or information signal. So this was the brief terminology we had talked about. So in today's class, we will mainly focus on 3 things that I have underlined here in this slide. One thing that we will be concentrating on, that is modulating signal. Another thing that we will be putting emphasis on, that is your carrier signal. And third thing is your modulated signal. So today we will talk about only these 3 things. That is, your information signal is nothing but your modulating signal. Then we have carrier signal, which will carry our information or modulating signal from one place to another place. And once you superimpose information signal and carrier signal, it becomes your modulated signal. Okay, so this is what we have again and again talked about. And another important thing that we discussed in the previous class was instantaneous value of any sinusoidal signal. So students, so this is the slide where I want to start with in today's class, after discussing briefly about the things that we have discussed in previous classes. So just a few slides back, I talked about the concept of modulation. So now in this slide, I am talking about the mathematical definition of modulation. See, students, in engineering, we have to understand two things in any subject. First thing is we have to understand the concept of the things that we are going to learn. And another thing is the concept, the physical concept that, or the abstract concept that we have learned, we have to correlate that concept with the mathematics. So mathematics will help us in formalizing our concept. So if we want to understand things in a better way, if we want to apply our concepts to systems, we need to give it a mathematical shape. So obviously we are very familiar with mathematical expression. So whatever we have thought of, whatever justification we have provided to our understanding, if we can formalize with the help of mathematics, then indirectly we prove that whatever we are thinking of is correct, if mathematics supports it. Okay, so if I talk about the mathematical definition of modulation, then see, in the previous slide, I mentioned this thing, that in case of modulation, your message signal or your modulating signal is superimposed with the carrier signal. So your message signal on the left hand side of the slide, also I have shown message signal, we have carrier signal. What we are doing, we are superimposing these two signals, and as a result we get modulated signal. Okay, so now how do we superimpose? So we superimpose our message signal onto the carrier signal in three ways. This superimposition can be done by changing the amplitude, or by changing the frequency, or by changing the phase of the carrier signal. This thing you have to basically keep in mind. Okay, so in the modulation, what we do, if you remember, I told you in the previous class as well. So if we have a carrier signal, say this is the carrier signal, okay, sinusoidal carrier signal, there are three things in this carrier signal. One is called the amplitude. Amplitude means the peak value of the sine wave. Okay. Another is the frequency. So since it is a sine wave, so its frequency is constant. Okay. And third thing is the phase. What is the phase? Phase means the beginning, the point at which your sinusoidal signal begins. So mathematically, if I represent your sine wave, then your sine wave looks like this: A sine omega ct plus phi. What is A? A is the amplitude of the sine wave. Omega c is the frequency of the sine wave, and phi is the phase of the sine wave. Okay, and if we represent these things graphically, then this is represented on the left hand side of the slide. Okay, so you see here that this carrier signal is a sinusoidal signal whose amplitude is fixed. Amplitude means peak value, means A is fixed. It is a constant quantity. Another thing which is fixed for this sinusoidal signal is the frequency. So the frequency of this sinusoidal signal is fixed. You already know that. Okay, and since this carrier signal is starting at a particular point, it means the initial phase is also fixed. So in the carrier signal, which is represented by a high frequency sinusoidal signal, there are three things which are constant. One is amplitude, another is frequency, and third is the phase. So this is our carrier signal. Now what we want to do, we want to vary either of these quantity. Okay, we will either change the amplitude of the carrier, we will either change the frequency of the carrier, we will either change the phase of the carrier. And whatever we change, the other two things will remain constant. Means if you change the amplitude, the frequency and phase of the carrier will remain same. If you change frequency, amplitude or phase will remain same. If you change phase, then your amplitude and other parameters will remain same. Okay, so two things I have talked about. One is the three parameters of your carrier signal, which is unmodulated. Second thing is that these parameters are constant, which can be varied. Now the question arises that how do we vary these values? So we have to vary the value of these parameters in accordance with the instantaneous value of the modulating signal. This is very, very important point that you have to keep in mind. Okay, what I want to say here, that we will be changing the characteristic of the carrier by instantaneous value of the modulating signal. So what does it mean? Let me explain to you people. See, this is our message signal. And I hope you know the meaning of instantaneous value. If I draw a sine wave, say this is a sine wave. Okay, this is a sine wave. Now, the peak value is the amplitude. Peak value is fixed. Now, what is the meaning of instantaneous value? We know that on the x-axis we have time. Okay, it is a time domain signal. Instantaneous value means the value at a particular instance. Okay, so if I ask that what is the value at t1, at t1 say this is the value, at t2 this is the value, at t3 this is the value. So values at particular instances, which I have indicated with 1, 2, 3. Okay, so instantaneous value of the modulating signal means value at a particular instance. Okay, so mathematically, if I represent sine wave with this equation, VCT equal to A sine omega CT plus phi. I told you what is A. I told you what is omega C. I told you what is phi. Now, I want to ask what is VCT. This VCT is nothing but the instantaneous value. Okay, means the value of this sine wave at a particular time t, because this is a mathematical equation. Whatever value of t you put, say if you put t1, the value of VCT will be VCT1. If you take the value of time as t2, the value of VCT will be VCT2, means at different instances of time. Okay, so this is the meaning of instantaneous value. So what we are doing mathematically in the definition of modulation, we are changing the amplitude or frequency or phase of the carrier signal in accordance with the instantaneous value of the message signal. Okay, things will be further clarified once we move forward. Okay, don't worry if some of the things are not very clear. So when we will finish off with the class, then things will be clear to all of you. Okay, so students, one more thing I want to emphasize here. I told you that your carrier signal will be a high frequency carrier signal. What about message signal? We have represented the message signal with the help of a sinusoidal signal. Okay, but see, practically it may not be always sinusoidal. Just for the sake of simplicity, just to make you understand clearly the concept of modulation, the message signal has been taken as sinusoidal signal, because the sinusoidal signal can be represented easily in the form of mathematics. Okay, though practically this message signal will never be sinusoidal, because it will be random signal. It will be some arbitrary signal. Just for making you understand, message signal has been taken as sinusoidal signal. But your carrier signal will always be sinusoidal signal in case of your analog communication. I hope all of you have understood this thing. Okay. So students, after discussing the mathematical definition of modulation, we will continue with the same thing, and we will talk things about things in a bit detail now. Okay, so as I told you that we can change the amplitude of the carrier, we can also change the frequency of the carrier, we can also change the phase of the carrier. Okay, so when we change the amplitude of the carrier in accordance with the instantaneous value of the modulating signal. Students, I am again and again repeating this thing. You have to keep these two things in mind. One is the instantaneous value of modulating signal. Another thing that you have to keep in mind is amplitude of the carrier when we talk about amplitude modulation. Okay, so amplitude of the carrier is varied in accordance with the instantaneous value of the modulating. In case of frequency modulation, the frequency of the carrier is varied, not the amplitude, not the phase. So frequency of the carrier is varied in accordance with the instantaneous value of the modulating. Similarly, in phase modulation, the phase of the carrier is varied. And how do we vary? In accordance with the instantaneous value of the modulating signal. So students, you look carefully in all these three definitions, that one thing is common, that we are doing the variation in accordance with the instantaneous value of the modulating signal, whether it is amplitude modulation, frequency modulation, or phase modulation. The only difference is, in case of amplitude modulation, the amplitude of the carrier is varied. In case of frequency modulation, the frequency is varied. In case of phase modulation, the phase is varied. However, the variation takes place according to the instantaneous value of the modulating signal. And instantaneous value of the modulating signal, I have already explained. In other words, like I will advise you people to mainly concentrate on amplitude modulation right now, so that you can understand things in a better way. So here now we will see that how actually your carrier characteristics are changed in accordance with your instantaneous value of the modulating. So on your left hand side, there is one figure. So at the top, this is our modulating signal, okay, which is varying with respect to time. Then the second signal is your carrier signal. So in amplitude modulation, where is the amplitude? The amplitude lies at the top of this carrier signal. This is amplitude, which is a fixed value. So this constant amplitude has to be varied in accordance with the modulating signal. So now what is happening in the modulating signal? The amplitude of the modulating signal is first increasing, or instantaneous value is first increasing, then getting maximum, then decreasing, then getting minimum, then maximum. Your modulating signal is changing like this. And your carrier amplitude is fixed. So what we have to do? The amplitude is to be changed. So what we have done, the amplitude of the carrier is varying according to your modulating signal. Earlier, the amplitude was constant, a constant line. After modulation, what we are doing, this constant line has been changed, or amplitude has been changed. How? By in accordance with the variation in the modulating signal, that is sinusoid. So the amplitude, which was a constant value before modulation, it has taken the shape of modulating signal after modulation. So this is the meaning of that is, we are changing the amplitude of the modulating signal in accordance with the instantaneous value, amplitude of the carrier in accordance with instantaneous value of the modulating signal. This is amplitude modulation. Now see, in the second last figure, this is frequency modulation. So in frequency modulation, the amplitude is constant. See, amplitude is constant. The phase is also constant. Okay. Now in frequency, what has to be changed? Frequency has to be changed. So how? See, in this figure, the frequency of the carrier is constant. Frequency is constant. Now we have to vary this frequency in accordance with this modulating signal. So what is happening? In this modulating signal, the value of the modulating signal is first increasing. So now what we have to do, we have to change the frequency of this carrier. So what is happening? The value of modulating signal is increasing first. Okay, so what is happening here? You see here, as the value of modulating signal is increasing, the frequency is increasing. Here frequency is highest at the peak. Okay, then the value of the modulating signal is decreasing, so frequency is also decreasing. Then the value of the modulating signal is again increasing, so frequency is increasing, then frequency is decreasing. So what we are doing, we are changing the frequency of the carrier in accordance with the modulating signal. So here amplitude of you can say modulating signal is increasing, so frequency is increasing. Here the modulating signal value is decreasing, frequency is decreasing. Here frequency modulating signal value is increasing, here also frequency is increasing. Here value decreasing, here frequency is decreasing. So in this case the frequency is changing, not the amplitude, not the phase. See carefully again, the amplitude is constant, amplitude of the carrier. Phase is constant, only the frequency is changing. This is your frequency modulation. Okay, so our modulating signal was first increasing, then decreasing, first increasing, then decreasing. In the same way, in the third, you can say in AM, your amplitude has changed accordingly. In FM, frequency has changed. Okay, and similarly, if you change the phase, then this kind of waveform will come. So here I would like to say one thing, that this frequency modulation and phase modulation waveforms appear exactly same to you people. Right now, what I will say that you can assume that frequency modulation and phase modulation, they are quite related with each other. Okay, so you need not worry about just now. You simply assume that the way variation takes place in frequency modulation, in the same way variation takes place in phase modulation, and they are related with each other. And you keep this thing in your mind, that amplitude of the carrier is varied in amplitude modulation, frequency is varied in case of frequency modulation, and phase is varied in case of your phase modulation. Fine. I hope now by looking at the types of modulation, all of you are clear about the concept of amplitude modulation, frequency modulation, and phase modulation. Fine. Now let us move forward. So students, before I move to amplitude modulation in detail, we must know the brief idea about the analog communication also. So if you remember, the name of our subject is analog and digital communication. Just now we have talked about only related to electrical communication. Now electrical communication is of two types. You can say that of the type analog and of the type digital. So we have analog communication, and another we have digital communication. Fine. So here just I will briefly touch upon the meaning of analog communication and the meaning of digital communication. And I brought this concept here just to familiarize yourself with the term. Otherwise, as the syllabus progresses, you will be able to exactly clarify the difference between your analog communication and digital communication. So students, I have shown you the block diagram of analog communication system. Okay, so here if you carefully look at this diagram, it is exactly same as we have seen in the basic block diagram of electrical communication system. The only difference is we have highlighted the word analog. So see, we have analog information source, we have analog modulation, we have analog carrier source, we have analog demodulation. Okay, so this is what you have to notice here. when we say analog communication, means our message signal or our information signal will be of the type analog. Fine. If we talk about the digital, you can say communication, in that case, this information source, it will be digital. It will be digital. Fine. And if our information source is of the type pulse, we call it as pulse communication. Okay. So if we say that my information source is of the type analog, my information looks like this. It is having analog, you can say, characteristic. If I say that my signal is of the type digital, then it can be represented in the form of ones and zeros. Say if this is 1, this is 0, this is 1, this is 1. So my information source will be having digital information. And if I say pulse, then my information source will be in the form of pulses. Okay. So this is the difference between your analog communication, digital communication, and pulse communication. Just for your reference sake, I have categorized various modulation techniques. In analog modulation techniques, we have amplitude modulation, frequency modulation, and phase modulation. So AM, FM, PM, these are under the category analog modulation technique. In pulse modulation, we have PAM, that is pulse amplitude modulation, pulse width modulation, and pulse position modulation. Similarly, in digital modulation technique, we have ASK, that is amplitude shift keying, then frequency shift keying, and then phase shift keying. Okay, so my motive behind this slide is to appreciate the fact that AM, FM, PM, these modulation techniques, they come under the category analog modulation technique. Okay, and rest of the things that we have in our syllabus, they come under these two categories, that is pulse modulation and another is your digital modulation. I hope this thing is clear. Okay, so in case of digital modulation, your information source will be digital. Your transmitter will have digital modulation technique. Your receiver will have digital demodulation technique. Okay, so I hope this concept is clear to each and every. So students, after discussing this concept of modulation and then talking about different types of modulation, now we move to amplitude modulation. So as I explained you that in amplitude modulation, what we will do, we will vary the amplitude of the carrier in accordance with the instantaneous value of the message signal. And if we do that, the amplitude of the carrier will take the shape of the message signal instantaneous value. So you can see here that the amplitude of the carrier has taken the shape of the your amplitude, or you can say voltage levels of your modulating signal. Okay, so this is conceptually that we have talked about up till now. So now we need to understand the things mathematically. Okay, so as I told you that conceptually we have understood. Now since I told you that your message signal has been represented in the form of sinusoidal waveform, your carrier has also been represented in the form of your sinusoidal waveform. We know the mathematical equation of sinusoidal wave. So why don't we formalize our concept with the help of mathematical equation? So here my objective is to derive the equation for the AM signal. AM means amplitude modulated signal. Here this word means modulated. Okay, means this one. This is our AM signal. Okay, so first one is our modulating signal. Okay, then second one is our carrier signal, and third one is our modulated signal. So when we say AM signal, it means amplitude modulated signal. And for getting modulated signal, we need two things. One is the carrier signal and another is the modulating signal. Okay, so now let us see one by one how are we representing things. So as I told you, this is our modulating signal. This is our modulating signal. So here this small v means the instantaneous value. You could have written it as like this also, small v with bracket inside bracket t, and we have a small m. Small m means message signal or modulating signal. This t has not been shown here just for the sake of compactness. Otherwise this t is implied here because this is time domain function. Fine. So this is our time varying message signal, which has been represented with the help of a sinusoidal wave. So here, what is capital VM? Capital VM is the amplitude of the message signal. This is the peak value of the message signal. Okay. Sine you already know. What is omega m? Omega m is the frequency of the message signal. Omega m is nothing but your 2 pi FM. 2 pi FM. And what is FM? FM is the frequency of this modulating signal. Okay. And you might be wondering that we haven't included phase here. Okay. So we have taken the phase as 0. Okay. So for the case of simplicity, we have taken 0 initial phase. That's why your instantaneous value of the modulating signal has become like this. So this is our modulating signal. I think you have understood the representation of modulating signal. Okay. Now see, this is the carrier signal. Small vc is nothing but the instantaneous value of the carrier signal. T is also implied here. Okay. As I told you, T is implied. Equal to capital VC is nothing but the amplitude of the carrier signal. Fine. Omega C is nothing but 2 pi FC, which is the frequency of the carrier signal. T is the variable. Here also we have taken our phase as 0. So this VCT is nothing but our carrier signal. So this is our carrier signal and this is our modulating signal. So students, try to understand here this thing that we have taken our message signal or modulating signal as the form of sinusoidal, and this was the logic behind this. We have taken sinusoidal representation for the case of simplicity. Otherwise, whatever message signal you take, that equation would have come here as modulating signal. Fine. So this is the initial background. Now we apply the definition of modulation. So what we do in modulation, amplitude of the carrier. Okay. Now you look at the equations carefully. You look at the equations. What is the amplitude of the carrier? Amplitude of the carrier is represented by VC. Amplitude of the carrier is VC. Okay. Amplitude of the carrier is varied in accordance with instantaneous value of the modulating signal. Now, which one is the instantaneous value of the modulating signal? Instantaneous value of the modulating signal is small Vm. This is instantaneous value. And this is your amplitude of the carrier. Okay. So we have to vary this amplitude in accordance with instantaneous. Or in other words, we have to superimpose the amplitude of the carrier and the instantaneous value of the modulating signal. So if you do that, this is what we get. We have to add the two things. We have to add the amplitude of the carrier with the instantaneous value of the modulating signal. I think this is clear to all of you. Capital VC is the amplitude of the carrier. Small Vm is the instantaneous value. This is not capital Vm. This is small Vm. Okay. And what is A? So if you are varying the amplitude of the carrier in accordance with the instantaneous value of the modulating signal, you get A. And what is A? A is the, you can say, the amplitude of modulated signal. A is this one. The peak value of the AM signal, the peak value of its top. Okay, this blue line. So let us see now. So I'm just going after this definition, I'm not moving here and there even a little bit. So what I'm doing, I'm superimposing amplitude with the instantaneous value. Vc is a constant. What is Vm? We substitute the value of Vm from here to here. So small Vm is nothing but capital Vm sine omega t. So we get Vc plus capital Vm sine omega mt. Then what we do, we represent, we take a term m equal to Vm by Vc. And what is Vm? Amplitude of modulating signal. This is amplitude of carrier. So if you use that, Vm, capital Vm becomes MVC. So this capital Vm has been represented by small m into Vc. Right now, you assume that m is some parameter. I'll tell you later on what is this m. So what we have got, Vc plus MVC sine omega mt. And you can see here that Vc can be taken common, and we get Vc common, Vc into 1 plus m sine omega mt. And what is this? This is A. Okay. And if you mathematically plot, or so if you graphically plot this thing, this equation, you will get this. Okay. I think you are able to understand that. For this is what we have got. This is nothing but this A, only this top line. Okay, I hope this thing is clear, that how actually we have superimposed the amplitude of the carrier signal and the instantaneous value of the modulator. So you need to concentrate on this part. This is very, very important in correlating the concept that we have developed with the equation that we have now proposed. I hope all of you have cleared with this thing. So now let us move forward. So as we saw in the previous slide, we obtained the value of A. Okay, so now, as I told you that we want to derive the expression for AM signal. Okay, so before we discuss further, let us talk about AM signal. As I told you that, how do we get AM signal? AM is nothing but amplitude modulated signal. Okay, so how does AM signal look like? Amplitude modulated signal. I told you, AM signal will be obtained when we change the amplitude of the carrier by keeping its frequency constant, by keeping its phase constant. Okay, so if I write the expression for AM, you let me write that, then you will be able to understand. It is VAM. This is nothing but the instantaneous value of the AM signal is equal to, since my sinusoidal representation is there, I take A as the amplitude of AM signal, amplitude modulated signal. Okay, which is in fact, just a minute, let me represent it in some different way. Let us not take this one. This is the instantaneous value of the AM signal. Fine. And since we are changing the amplitude, okay, so that amplitude will be some varying. So let us take that amplitude as VAM. Okay, and we know that its frequency and phase is constant. So we take sine. Frequency, how much is the frequency? It is same as that of the carrier. So we take that as omega CT, and phase is also same. That is, say, phi. And since we have taken phi as 0, that's why it has not been shown. So this is the general expression of any amplitude modulated signal. This we already know, sine omega CT plus phi, that is already known to us. All that we want is the value of this VAM, that is amplitude of AM signal. And the expression for this VAM, we have already derived in the previous slide. See, what was that? VAM or A, this one, VC into 1 plus M sine omega MT. So if you substitute this, see, look at this. This is one and the same thing that I have shown here. Okay, so what is happening here? This is our instantaneous value of AM signal. This is amplitude of AM signal. and this is frequency of AM signal, which is nothing but equal to the carrier frequency. Phase we have taken 0, otherwise this would have come here. Now, once you substitute the value of A, you get this one. Vc into 1 plus m sin omega mt. So for A, you have got this sin omega ct as it is reproduced here outside the bracket. Okay, so this is the expression for your amplitude modulated signal. Look at these two terms carefully. So this is instantaneous value of the resulting amplitude modulated wave. This is the amplitude of the resulting amplitude modulated signal. And this is, you can say, that sine part of your sinusoidal equation, that is sin omega ct. Fine. So this is the mathematical derivation of your AM signal. Very simple. I hope all of you have understood, and you all know how to draw the sine wave from its equation. If you put different values of time in this equation and you solve for its graph, you will get the same equation, this one. You will get same waveform, same graph. Okay. And if I tell you the simple method to represent this graph of AM signal, I'll just tell you. Okay, now first we need to understand how do we draw sine wave. So for sine wave, what do we write? We write V equal to A sine say omega t. This is how we represent a sine wave. And how do we draw it? A is a constant amplitude. So what we do, we draw constant amplitude. Okay, and then we have omega is a constant frequency. Then in between we draw the constant frequency inside this amplitude like this. My drawing may not be that appropriate, but just to make you understand. Okay, so this is this one and constant frequency comes here. Fine. Now what is happening? Is our amplitude constant? No, our amplitude is of the type this. This is our amplitude. Okay, so if we want to draw this, so first we have to draw amplitude. So if we draw amplitude, this one, this we have draw amplitude, and this amplitude is which one? The above one. See, we all know that in sine wave we have positive values and we have negative values as well. Zero line is here. This is zero line. We have positive and negative. Okay, and this graph that you are observing here, this is only positive. Where is the negative part of sine? Negative part is here. Okay, negative part is reverse of positive. Means if this is our zero line, this is our positive part. The negative part is mirror image of positive part. So if we take the mirror image, it looks like this. This one, mirror image will look like this. Okay, so what we have done, the way we had represented amplitude, positive part, negative part, and after doing that, we plotted sine wave inside that. So similarly, we will do here. We are drawing the positive part and we are drawing its mirror image. Then what we are doing, we draw the sine wave and we will draw it here like this. So whatever contour all of you have got, you draw sine wave inside that contour like this. Like this. So your peaks are no longer constant because those peaks are now varying in accordance with your modulating signal. That's it. This is how we get AM signal. This is your, you can say, amplitude, its mirror image. If you draw this equation graphically, you'll get the same kind of thing. And inside you have the carrier. So if you want to look at it more precisely, you can see to this waveform. You see here, this is my positive part of AM signal. This is its mirror image in the negative side. And in between what we have done, we have drawn the carrier wave touching all those, contour of your amplitude. Okay, so if I erase it, you'll be able to see it. I hope all of you have understood how to derive the equation of AM signal and how to visualize AM signal and how to draw AM signal by looking at this. I hope everybody is clear of this thing. So students, after looking at the derivation of the expression of AM signal regarding instantaneous voltage of AM signal, now we move forward. We would like to extract some more information out of this equation. And see, if you look at this expression carefully, you see there are two things here. There are two signs. One is sine omega mt and another is sine omega ct. So if we multiply sine omega ct inside this bracket, we get some more terms. You also multiply with vc, so we get three terms. One is vc sine omega ct. Let me clarify it in a more better way. This sine omega ct, it comes here. Vc also comes here. We get this term vc sine omega ct. Okay, and then this vc comes here, sine omega ct comes here. We get this one m vc. Okay, then sine omega ct, sine omega ct into sine omega mt. We get this as the second term. Okay, and all of you are very good in mathematics. You know that how to simplify this trigonometric relationship. So one is vc sine omega ct, one term. Another is plus mvc sine omega ct sine omega mt. Okay, so we have sine a sine b, such kind of terms here. So we know that this term will come when we have cos of, I hope you remember this thing, that 2 sine A sine B. If you have such thing in the mathematics, you look at this. I have shown it here. Sine x sine y, this is equal to 1 by 2 cos of x minus y minus cos of x plus y. So if you apply this identity, you get this thing, that mvc by 2 cosine of omega c minus omega mt minus mvc by 2 cosine of omega c plus omega m into t. So this is nothing but the same expression that we have seen here, but a bit elaborated one. And this expression is also very, very important. We will talk about this expression later on, but you memorize this thing that there are three terms. In the first term, we have omega c, that is carrier frequency. In the second term, we have omega c minus omega m, means something less than carrier. Something has been subtracted from the carrier. And the third term is omega c plus omega m, means something is added into the carrier. And what we are subtracting, what we are adding, we are subtracting nothing but the modulating signal frequency, and we are also adding the same modulating signal frequency. So one we have carrier frequency, another is omega c minus omega m, and third one is omega c plus omega. Okay, so these two expressions, both these expressions are very, very important with regard to your amplitude modulation. Now let us move forward. So students, this expression I have already explained to you, and you have to basically remember two things here. One is this waveform is with regard to AM signal, that is amplitude modulated signal, and another important thing is time domain representation. Okay, so what is the meaning of time domain representation? Time domain representation means your x-axis is with respect to time. So if I ask you to draw a sine wave in time domain, your sine wave looks like this, and you say that x-axis is nothing but time and your y-axis is nothing but some amplitude, say some voltage V. This is your time domain representation of the sine wave. Okay, so what I have shown here, you people, in this slide is the time domain representation of AM signal. So where my x-axis is in time, and on y-axis I have my voltage, instantaneous value of the voltage of AM signal, that is nothing but VAM. So this graph I have already explained in the previous slide, and if I go back, this is nothing but the same thing. Okay, just me go back one more slide. Just a minute. This one. Okay, I explained this VAM is the instantaneous value, and A is the amplitude which is varying, and omega CT is the your carrier frequency. Okay, so see, this is nothing but the amplitude of the AM signal, instantaneous value of the amplitude, like this one which has been shown on the left hand side. And once we draw that, we have to draw its mirror image. This is the mirror image, as we have in sine wave, that this is positive part, this is negative part, its mirror image. Fine. So same is the case here, that this is your VC plus VM sine omega t, and this is minus of VC plus VM sine omega t. The way we have, this is plus VC in the sine wave. Okay, plus VC. And what is this? This is minus VC. So same is the case here. So if you plot this equation, you will get the same kind of thing. This the method that I have explained, it is method that will help you in draw it comfortably. And so once you have drawn this contour, you can draw the sinusoidal waveform inside this. Okay, touching the contour. And this is how you get this waveform. Okay, so this contour, I am talking about the term again and again, contour. So this contour is, having one specific name that we call as envelope. Okay, what is the purpose of envelope? Envelope covers whatever is there inside it. Okay, so this contour, what I am drawing now, this contour is called AM envelope. This is AM envelope. Okay, envelope of AM signal. And what it is enclosing? It is enclosing the carrier part. Okay, and a few terms which have been shown here that you can clarify just by looking at it. Fine. So see, this part is nothing but your modulating signal shifted upwards. Okay, fine. And this I told you that this is your mirror image. Fine. This is nothing but your modulating signal. Okay, so in a way you can say that, since see, if I go back, so what was happening here? See, just a minute, one more slide, this one. Yeah. So here what was happening? VC plus VM means what we are doing in the modulating signal, we have added the carrier amplitude. So obviously if you do that, your signal will shift upwards. Okay, so if you add the carrier VC, so this is what we have done, VC, this is nothing but your instantaneous value of the modulating signal. So if you add something, obviously your signal will be shifted in the amplitude, shifted upwards, and this is the mirror image. Okay, so what will be its peak? The peak of AM signal will be V max. Okay, the positive peak, and this is the minimum signal, that is V min. Okay, and I think all things, if you look at this thing carefully, you'll be able to observe many other things also. Fine. So this is your time domain representation. So I hope you have looked into this term very carefully, time domain representation, because I am to discuss one more thing in the next slide related to AM signal only. So I hope this thing is clear. So now let us move forward. So this is something that I wanted to understand, wanted you to understand, that is frequency domain representation. Okay, and frequency domain representation of what? AM signal. And what was there in the previous slide? Time domain representation of what? AM signal. It means this is also AM signal, and in the next slide also we have AM signal. So this is also AM. I have reproduced it on this slide. This is also AM. Both are AM. Both are AM. This is also AM. This is also AM signal. This is also AM. Now the question arises that why they are different if they are representing the same AM signal. They are different because we are looking at the same AM signal from two different eyes. Okay, say like if we have in normal life also, if two people look at the same person, they will look at that person with different viewpoint. Okay, but by looking at the person with two different viewpoint, does it change the person? No, never. So similarly here also, students, I want to tell you that time domain representation and frequency domain representation are nothing but the two different ways to look at the same thing. And here that same thing is AM signal. This is also AM, this is also AM. The only difference is in the first figure we have represented AM with respect to time, whereas in the second figure we have represented our things with respect to frequency. Means in the first figure our x-axis is with respect to time, and in the second figure our x-axis is with respect to frequency. So obviously if you change the axis parameter, like if your axis parameter is time, obviously graph will be different. That is your for time. If your axis parameter is different, say for frequency, your graph will be different. But signal remains same. Only the graph is changing. Okay, so every signal can be represented in two domains, in time domain as well as in frequency domain. Okay, so if I take the example of simple sine wave, if you represent your sine wave in time, your sine wave looks like this. This is your time domain representation of sine. Now, if we want to represent the same sine wave in frequency, means in frequency domain, if my x-axis is in frequency, then how does this sine wave look like? So in frequency domain, we know that in sinusoidal signal, there is only one frequency. So we will have only one line, okay, one impulse, which indicates the frequency of that sinusoidal signal, which says that FC is that frequency. So this is also sine wave, this is also sine wave, but this is your sine wave represented in time, this is your sine wave represented in frequency. Okay, when we say sine wave, normally we are in a habit to visualize things in time. We are not so, habitual of visualizing things in frequency, but in communication, frequency is very, very important parameter. I'll tell you why it is important in the coming classes. Okay, so this is your sine wave in time domain, this is your sine wave in frequency domain. If I tell you some more thing that will help you in understanding this time domain and frequency domain representation, all of you have studied Fourier series in your signal and system. Okay, so if you obtain the Fourier series of sine wave, you will get one value. Okay, what does it mean? That there is only one frequency. And if you obtain the Fourier series of square wave, you will get infinite values. It means there are infinite frequencies. Okay, so what does your Fourier representation do? Your Fourier representation convert your signal from time domain to frequency domain. If your signal is periodic, you use Fourier series. If your signal is non-periodic, you use Fourier transform. Otherwise, this representation is one and the same thing. In communication, frequency domain representation is also very, very important because of spectrum. All of you have learned or in fact listen to the term bandwidth, listen to the term spectrum. So the spectrum bandwidth, it comes from nowhere else but from your frequency domain representation. Okay, so just we need will not enter into much details of Fourier series, Fourier transform here. Now the question arises that how do we represent AM signal in frequency domain easily? I told you for sine wave there is a single frequency. Single frequency is represented by impulse. Okay, now let us see how many frequencies or how many sine waves are present in AM signal. So let us go to previous slide. See here, this expression is now important. In this AM signal, there are three sine waves. One is sine omega CT. Okay, another is cosine omega C minus omega MT. Another is cosine omega C plus omega MT. And we know that sine and cosine are nothing but one and the same thing, only there is a difference of phase. Okay, otherwise frequency wise, whether sine or cosine, they have only one frequency. So but in AM signal here we have three sine terms, or one sine or two cosine terms. It means how many frequencies? Three frequencies. What is the frequency of this term? The frequency of this term is FC. What is the frequency of second term? FC minus FM. Okay, what is the frequency of third term? FC plus FM. FC plus F. So it means in AM signal, AM means amplitude modulated signal. After modulation, we have got three frequencies. One is FC, another is FC minus FM, and another is FC plus FM. So due to modulation, our frequencies, three frequencies have been obtained. And what was the frequency of message signal? Message signal frequency was FM. Carrier signal frequency was FC. Okay, and because of modulation, we have got three frequencies: FC, FC minus FM, FC plus. Okay, so this is the change what modulation has brought. So in this AM signal, you have to notice the presence of these three frequencies, and each frequency is represented by an impulse. So same thing has been represented here. See, this is FC. Okay, obviously FC plus FM will lie at the right hand side of FC, and FC minus FM will lie towards left hand side, and FC plus FM towards right hand side. So this is FC, FC minus FM, FC plus FM. Obviously gap will be FM. Okay, now what is FC? FC is the carrier frequency. Okay, FC plus FM means something has been added to carrier frequency. We call this FC plus FM as USB, that is upper side band. And FC minus FM, FM is subtracted, we call it as lower side. And this is carrier. So my dear students, because of modulation, if you observe modulation, AM modulation in time domain, this is what we have observed. That is, in time domain, the envelope of the carrier has taken the shape of the modulating signal. And if you observe the same AM in frequency domain, then what has happened? We have obtained three frequencies. One is the carrier frequency, another is the upper side band, and third one is the lower side band. FC, FC minus FM, and FC plus FM. If you observe in the frequency domain. And I was talking about bandwidth in frequency domain. Obviously, what is bandwidth? Bandwidth means highest frequency minus lowest frequency. And what is the highest frequency in AM signal here? FC plus FM. What is the lowest? FC minus FM. If you subtract, you get twice of it. Okay, so this information you could get only and only from frequency domain representation by observing the various frequencies and subtracting the highest frequency and the lowest frequency. So it means the bandwidth of amplitude modulated signal is how much? 2 times the modulating signal frequency. Okay, so this is the information that you have got from frequency domain representation, and from time domain representation we have got the information regarding envelope of the AM signal. I hope this thing is clear to each and every student. Okay, so students, after this frequency domain representation, now let us move forward. So this is your assignment number 1. All of you have to submit this assignment through classroom. Okay, and here you have to explain about various modes and media of electrical communication, and I have shown you various hints also, the main points that you have to cover in this assignment, that is your wireless media or wireless modes, that is ground wave propagation, sky wave propagation, space wave propagation, etc. The word etc. has been put just so that you also search and give some thought to it. In the wired media, we have twisted pair, coaxial cable, optical fiber. So whatever media, you know, help us in communicating, though it in wired media or wireless media, you have to explain their principle, you have to explain their frequency ranges, you have to explain their applications, uses. Please make this assignment as very exhaustive one, and that will supplement whatever I have taught you in this subject up till now. So that's all for today's class. Thank you very much.